Hi everyone, this is Professor M. Science, and today I want to build the eigenvalues and eigenfunctions of the 3D isotropic quantum harmonic oscillator in another one of our videos on rigorous quantum mechanics. If you've been following us for a while, you will probably know that we have already calculated the energy eigenvalues and eigenvectors of the 3D isotropic oscillator in these videos. We found that the energy eigenvalues of the 3D isotropic oscillator are quantized and that we can write the energy eigenfunctions as the product of three 1D oscillator energy eigenfunctions. So you may wonder, why would we want to do this again? Well, today we're going to study the 3D harmonic oscillator with a different approach. We're going to treat it as a central potential. As expected, we will find that the energy eigenvalues are exactly the same as the ones that we found in the other videos. But the energy eigenfunctions are going to look very different. Today, we're going to write them so that they're also eigenfunctions of orbital angular momentum, which means that they will be given in terms of spherical harmonics. So, a quick disclaimer. What we're going to do today has to build on the rather long mathematical solution of the eigenvalue equation of the 3D oscillator as a central potential. So I would encourage you to check out the corresponding video if you haven't done it yet. So let's go.
Okay, so what do we know about the three-dimensional isotropic quantum harmonic oscillator? Working in the position representation, the corresponding Hamiltonian H has a kinetic energy term and the potential energy term has a quadratic form, which in 3D can be separated into a term proportional to x squared, a term proportional to y squared, and a term proportional to z squared. We are interested in an isotropic oscillator, and this means that the frequencies are the same along each Cartesian direction, and we call them simply omega. We can then rewrite the Hamiltonian with the same kinetic energy. And for the potential energy, we can take this common factor multiplied by this sum of squares. And using spherical coordinates, this is simply the square of the distance r from the origin. And this means that the Hamiltonian of a three-dimensional isotropic quantum harmonic oscillator has the usual kinetic energy term and a potential energy term that is equal to 1/2 m omega squared r squared. The dependence in R means that the three-dimensional isotropic quantum harmonic oscillator is described by a central potential. So the eigenvalue equation of the Hamiltonian is given by H, acting on the eigenfunction, and equal to the eigenenergy times the eigenfunction. And as always, we're interested in finding these eigenvalues and these eigenfunctions. The mathematical solution of this eigenvalue equation is rather involved, but it's also interesting. For example, it involves a power series expansion. So for the full mathematical details, we have a companion video where we go over the solution step by step. I really do recommend that you watch it now if you haven't done it yet, because today we will start from there to build a few examples of the eigenvalues and eigenfunctions and explore some of their properties. One important feature of the eigenfunctions is that they can be chosen to also be eigenfunctions of the L-squared orbital angular momentum operator like this, where remember that the quantum number L can take any non-negative integer value. And the eigenfunctions can be chosen to also be eigenfunctions of the Lz orbital angular momentum operator like this, where for a given L, the quantum number ml can only take one of the values between -L and L in steps of 1. With this knowledge, we can rewrite the eigenvalue equation for the Hamiltonian, where we label the eigenfunctions and eigenvalues with the appropriate quantum numbers like this. We see that the eigenfunctions depend on the orbital angular momentum quantum numbers L and ml. And for every combination L-ml, we have a spectrum of energy eigenfunctions labelled by the additional quantum number k. Now, in principle, the energy eigenvalues can also be labelled by these three quantum numbers, but we find in the videos on central potentials that they actually only depend on k and L, but not on ml. An important side note, there's a link in the description to a video where we've already solved the 3D isotropic quantum harmonic oscillator, but we take a different route using Cartesian coordinates and tensor product state spaces. In that case, the energy eigenfunctions are not eigenfunctions of orbital angular momentum, so they take a different form to the form that we are going to explore today. So, as an interesting exercise, I would really encourage you to go and compare both sets of eigenfunctions. Right, so let's start with a quick refresher based on the companion video where we solve this eigenvalue problem mathematically. Remember that the full eigenfunction psi is given by the product of a radial part and an angular part. This angular part here is the same for any central potential and is given by the spherical harmonics, which are the orbital angular momentum eigenfunctions and only depend on the quantum numbers L and ML. The radial part here depends on the precise form of the radial potential and is labelled by the quantum numbers K and L. What we do in the companion mathematical video is to figure out this radial part of the eigenfunction, and doing so takes a rather large number of steps. First, we define a new function u, which is related to the original radial function by this equation. Then, considering the limit of large R, we define another function v, which is related to the u function via this relation. And then we express the function v in a power series like this in terms of expansion coefficients c. And the lowest power s in the expansion is equal to L plus 1. Finally, the expansion coefficients c obey a recurrence relation between cq plus 2 and cq equal to this prefactor times this long numerator divided by this long denominator. We also have that the first non-zero expansion coefficient is C0, while C1 vanishes. And all other expansion coefficients can be constructed from these two using the recurrence relation, and in particular, as C1 vanishes, we can immediately conclude that all odd expansion coefficients must also vanish. For the even expansion coefficients, we will always be able to write them in terms of C0. So we can then complete the solution, fixing C0 by normalization of the wave function. And that's it. This is the strategy that we will follow in this video to build the eigenfunctions. First, we will determine what these CE expansion coefficients are, and then from those we can construct V. Once we have v, we can construct u. Once we have u, we can construct the radial function. And once we have r, we can finally build the complete eigenfunctions. With this recipe, we can build any eigenfunction that we want. And in this video, we look at a few examples of how to explicitly do this step by step. So as we just discussed, we need to normalize the wave function to fix the C0 coefficient. The full wave function obeys the standard normalization condition, so we could fix C0 by imposing that condition. However, in the videos on central potentials, we discussed that we can separately normalize the radial part of the eigenfunction and the angular part of the eigenfunction. Indeed, we have already built the spherical harmonics such that they themselves are normalized. So in principle, we can fix C0 by using this normalization condition for the radial part of the eigenfunction. But in the video on the radial equation, we found that we can equivalently normalize the u function using this relation. The original normalization of the radial function involves the r squared here. But the normalization in terms of the u function does not. So this expression is in general simpler. So today we will normalize the wave function and fix C0 using this u integral. Before we start building eigenfunctions, we also need to discuss eigenvalues, again drawing from the results in the companion video. The eigenvalues are in principle labelled by the indices k and l and given by this expression. However, we can see that k and l only appear together as a sum here, so we can define a new collective label n, and then the eigenvalues can be labelled by this single label en, and are given by h bar omega times n plus 3/2. On top of that, we know that the angular momentum quantum number L can take non-negative integer values. And we also found in the companion video that K can only take non-negative even values. So from these, we can conclude that N can take any non-negative integer value. We can actually say more, starting from the fact that N is equal to K plus L. Let's start with N equals 0. This will be the ground state, and the only possible values are K equals 0 and L equals 0. For the first excited state, N equals 1, as K can only be even and non-negative, then it must still be 0, and this means that L must be 1 in this case. For N equals 2, we now have that K can be 0, in which case L must be 2, or K can be 2, and then L must be 0. And we could continue in this fashion for any N. Okay, we're now ready. In the rest of the video, we are going to look at a few examples of the eigenvalues and eigenfunctions of the 3D isotropic quantum harmonic oscillator. Let's start with the eigenvalues, and let's first consider the ground state n equals 0. If we look at the expression for the energy up here, the ground state energy is equal to 3/2 h bar omega. And I would now encourage you to compare this with the ground state energy that we got in the video where we solved this problem using Cartesian coordinates. And you will be able to confirm that, surprise, surprise, we got exactly the same energy. Sticking with the ground state, let's now turn to the eigenfunctions. The first thing to remember is that for n equals 0, we've just established that k is 0 and that L is also 0. To build the eigenfunctions, we now have a rather large number of steps, and the first one is to determine the expansion coefficients using the recurrence relation up here. First, remember that we can write the even expansion coefficients in terms of C0, and we can start with the first one corresponding to Q equals 0. Inserting this value of Q inside the equation at the top, we get C2 in terms of C0. We now insert these values of N and L into the recurrence relation, and replacing all Q's, L's and N's by zeros, we get this very long expression. These two terms add up to 3/2 h bar omega, and we've just found that the ground state energy up here is also 3/2 h bar omega. This means that we can cancel this term with this term, and this expression vanishes. This means that C2 is equal to 0. Given the recurrence relation, once we have a vanishing even expansion coefficient, all higher order even expansion coefficients also vanish. Remember also that all expansion coefficients vanish for odd Q. Putting these results together, we have that all expansion coefficients CQ are 0 for any positive Q. In other words, the only non-zero expansion coefficient for the ground state is indeed C0. The next step is to build V, for which we use this expression. As K and L are 0 for the ground state, we label V with the subindices 0, 0. Next, as we've just established that all expansion coefficients are 0 apart from the first one that corresponds to Q equals 0, then this sum has a single term, which leads to this expression. Finally, as S is equal to L plus 1, but L is 0, then the power of R is simply 1. And this means that we get that V00 is equal to C0 times R. Okay, the next step is to build u from v using this relation. Inserting the expression we got for v00 into this equation, we get u00 as equal to c0 times r times the Gaussian. At this point, we have to normalize the wave function to fix c0, and we've argued that to do so, we will use the normalization condition on the u function as shown up here. Rewriting it for our case, we get this. And we can now use this expression for u00 up here, and we end up with this new integral. We're now going to use a standard Gaussian integral, which you can look up in your favorite table of integrals, and which is equal to this. Now, if we compare this exponent with our exponent up here, we can identify a as equal to the square root of h bar over m omega. With this, we can evaluate the integral to get the absolute value squared of c0 multiplied by this constant. Isolating c0, we get that it's equal to this expression where I have made some trivial rearrangements. Note that I have also made a phase choice such that we end up with a real positive constant. With this result, we can rewrite u00 as equal to the prefactor times r times the Gaussian. And we're almost there. The next step is to go to the original radial function, which is equal to 1 over r times u. And using the expression for u that we just derived and inserting it in here, we can write the radial function r00 and end up with this prefactor times this Gaussian. Finally, the full eigenfunction is given by the product of the radial function and the corresponding spherical harmonic, as shown up here. In our case, as L equals 0, then ML only has one possible value, which is also 0. Using the results from the video on spherical harmonics, y00 is equal to 1 over the square root of 4 pi. We can next insert this expression for the spherical harmonic all the way up here, and this expression we just found for the radial function into this term. And we end up with the ground state wave function of the three-dimensional isotropic quantum harmonic oscillator being equal to this prefactor times this Gaussian term. The ground state is non-degenerate, so this eigenfunction is unique. And indeed, if you compare this with the ground state that we got in the other video where we solved this problem in Cartesian coordinates, then you will be able to confirm that we got the exact same eigenfunction. Moving on, it is great to have the mathematical expression for these eigenfunctions, like the ground state here, but we also want to visualize them. Unfortunately, we cannot fully visualize them because they depend on 3 coordinates, which means that we would need a 4-dimensional space to plot them. So what we will do instead is to separately visualize the radial part and the angular part. This is a depiction of the ground state eigenfunction. The radial part on the left here is purely real and shows that the eigenfunction decreases in magnitude as we move away from the origin of the central potential. Specifically, its shape is described by a Gaussian function. Moving to the angular part on the right here, it is an eigenstate of orbital angular momentum, and in this particular case, it is the y00 spherical harmonic, which is simply a constant. If you need a refresher of how to plot spherical harmonics, by the way, we have a video that does just that, and we've linked it in the description. But briefly, as they only depend on angular variables, we plot them on the unit sphere and use a red, white, blue color gradient scale, with red being positive, white represents 0, and blue corresponds to negative values. In this case, we get a uniform red sphere because the y00 spherical harmonic is a positive constant. And overall, the ground state eigenfunction takes its maximum value at the origin of the central potential and then decays away from the origin, and it does so isotropically. Let's now turn to the first excited state, and as the procedure is analogous to what we just did for the ground state, we will move quicker through the calculations, but I do encourage you to fill in the gaps and to make sure that you understand every step that we take. Let's again start with the eigenvalues, and we now consider n equals 1. The energy E1 is equal to 5/2 h bar omega. Again, I encourage you to compare this result with the corresponding one in the video where we treat this problem using Cartesian coordinates, and you should find that they are identical. Let's now turn to the eigenfunctions. The first question is, how can we get n equals 1 as a combination of k and del? We've just established that this arises from having k equals 0 and l equals 1. We next consider the first term of the recurrence relation, which is given by q equals 0. This term gives us C2 in terms of C0. And using the values of q, l, and n that we have, we get this very long expression. These two terms add up to 5/2 h bar omega, and the first excited state energy up here is also 5/2 h bar omega. So we can cancel this term with this term, and this means that C2 is equal to 0 again. So, for the first excited state, the power series again has all expansion coefficients CQ equal to 0 for any positive Q. And this means that again, the only non-zero expansion coefficient for the first excited state is indeed C0. The next step is to build V using this expression. We have that V01 has a single term, as S is equal to L plus 1, and now we have that L is equal to 1, then the power of R is 2. And this means that we get that V01 is equal to C0 times R squared. The next step is to build U from V using this relation. And we get that U01 is equal to C0 times R squared times the Gaussian. We again determine C0 by normalizing the function U. Inserting the expression we have for U into the normalization integral, we get this expression. We can again evaluate this expression using a standard Gaussian integral, and skipping a few manipulations, we get this. Now, rearranging, we get that C0 is equal to this expression, where I have again made a phase choice such that we end up with a real positive constant. With this result, we can rewrite U01 as equal to this prefactor times R squared times the Gaussian. Going to the original radial, we end up with this prefactor times R times this Gaussian. Finally, the full eigenfunction is given by the product of the radial equation and the corresponding spherical harmonic, as shown up here. In this case, as L equals 1, then ML has 3 possible values. Using the results from the video on spherical harmonics, we have that y1 minus 1 is equal to this expression. y10 is equal to this expression, and y11 is equal to this other expression. This leads to 3 distinct eigenfunctions for the first excited state. The first one is psi01 minus 1, and is given by this combined prefactor, the r-dependent terms and the angular dependent terms. The second one is psi010, and is given by this combined prefactor, the r-dependent terms, and again the angular term. And the third is psi011, which is given by this other combined prefactor, the r-dependent terms, and the angular terms. We therefore have a triply degenerate first excited state for the 3-dimensional isotropic quantum harmonic oscillator. Now this is an interesting bit. As the first excited state corresponds to a degenerate energy eigenvalue, then the corresponding energy eigenfunctions are not uniquely defined. Indeed, if you compare these 3 energy eigenfunctions to the corresponding ones we find in the video where we solve the 3D harmonic oscillator using Cartesian coordinates, you will find that, lo and behold, they are actually different. In particular, in today's video, we've chosen the energy eigenfunctions to also be eigenfunctions of the orbital angular momentum, which leads to these expressions in terms of spherical harmonics. By contrast, in the other video where we solved this problem using Cartesian coordinates, we don't really use orbital angular momentum eigenfunctions, and as a result, they look different. However, we do know that we can always make linear combinations of eigenfunctions corresponding to a degenerate eigenvalue to obtain equally valid eigenfunctions. And you should now go and try this out and try and relate today's results with those that we got in the video where we used Cartesian coordinates. Right, let's finally draw the first excited state wave functions. Here I'm showing the radial part, which is the same in all three eigenfunctions. It vanishes at the origin here. It has a maximum at some finite distance from the origin right here. And then it decreases in size as we move away from the origin of the central potential. The angular parts are different and are given by the corresponding spherical harmonics. This here shows the radial part we've just discussed, together with the y1-1 spherical harmonic. To help with the visualization, we can make the diagram of the spherical harmonic rotate like this. And the y1-1 spherical harmonic is a complex function, and we're plotting both its real and its imaginary parts. And again, if you need a refresher about how exactly we plot the spherical harmonics, you can check out the corresponding video that we've linked in the description. This here shows the radial part together with the y10 spherical harmonic. In this case, the spherical harmonic is a real function that is spherically symmetric. And this here shows the radial part together with the y11 spherical harmonic, which we can make rotate, and which has both real and imaginary components. We could repeat the same exercise for higher excited states, but now that you've seen how it works for the first few, you will be able to calculate the eigenfunctions for any other state yourself. To encourage you to explore this further, I will finish the video by showing the results for the second excited state that corresponds to n equals 2. The energy of the second excited state is equal to 7/2 h bar omega. We've seen earlier in the video that there are two possible choices of k and l that give this value of n. The first possibility is k equals 0 and l equals 2. From this value of l, we get these 5 possible values for ml. Overall, this means that we will end up with 5 eigenfunctions. For ml minus 2, we get psi 02 minus 2. For ml equals minus 1, we get psi 02 minus 1. For ml 0, we get psi 020. For ml equals 1, we get psi 021. And for ml equals 2, we get psi 022. But we can also get n equals 2 with k equals 2 and l equals 0. In that case, ml equals 0. So this second case leads to a single eigenfunction, which is psi 200. Overall, what we see here is that the second excited state is 6-fold degenerate. Here I'm showing you a plot of the radial functions associated with that second excited state. The figure on the left corresponds to the case when k equals 0 and l equals 2. In this case, the series solution again has a single non-zero term corresponding to the C0 expansion coefficient. The radial function vanishes at the origin here. It has a maximum at some finite distance from the origin here, and then decreases in size as we move away from the origin of the central potential. This radial function is shared between 5 distinct eigenfunctions, whose angular part is given by the L equals 2 spherical harmonics. The figure on the right shows the radial function when k equals 2 and L equals 0. In that case, the series expansion has two non-zero expansion coefficients, C0 and C2. The resulting radial function is positive at the origin right here. It then becomes negative beyond this point, and it approaches zero again as we move away from the origin. This radial function is associated with a single eigenfunction whose angular part is given by the L equals 0 spherical harmonic.
When we treat the 3D isotropic quantum harmonic oscillator as a central potential, its energy eigenfunctions are also eigenfunctions of orbital angular momentum. Now, as a fun follow-up, I would encourage you to compare the results that we got today to those that you get if you treat the 3D oscillator as the tensor product over three 1D oscillators. And you're going to see that the energy eigenfunctions take a rather different form. And as always, if you liked the video, please subscribe.